Thanks very much for coming along to your Turkey seminars again. Today's speaker is Dr. Ritabrata Dobe, our new Marie Curie Fellow. Rita, I'll let you introduce yourself.
So, in terms of introduction, there's not much more to add except for the fact that I'm a new Marie Curie Fellow in the department. I work with John, and this presentation has not much to do with what we are doing at this point of time. It's more of like a recap of what I used to do previously when I was a postdoc in Italy. So at the outset, apologies for this supremely underwhelming title for a Friday afternoon seminar. It was like a pre-coffee Monday morning title, but what we will do is we'll be looking at the effects of hydrogen on the rheology of carbonates and potential implications for underground hydrogen storage. So firstly, why do we care about hydrogen? So we all know that there's an urgent need to decarbonize the energy sector, and hydrogen is a potentially big player in that sector because it is carbon-free, it is a source of green energy. But the problem is traditional methods of creating hydrogen, such as steam reforming, they're not very efficient because you need more energy to be input compared to like the final output in terms of hydrogen. But over the last 20 years or so, there's been a lot of studies in geological settings whereby it's been demonstrated that fluid rock interactions such as serpentinization, these continuously produce hydrogen in the Earth's subsurface or nearer to the surface. And these require very little to almost no energy input. And they operate by a very simplified redox reaction that you can see here, this one here. So it's basically conversion of iron 2 to iron 3 and the reduction of water that produces hydrogen. It's not as simple as that, but like roughly if we have to simplify it, it's this. And currently there's a lot of investment and a lot of research effort going into attempts to stimulate these sort of reactions such as serpentinization at shallower PT conditions so that it may potentially be looked at as a source of fuel. So I have a video here, if it works. It does not. It does. So this is an abandoned chromite mine in Albania. And it used to be like chromite hosted in petrographic, but then it got flooded and abandoned. But now if you look at this mine, it's got a lot of these like bubbling pools, and all these bubbles are near pure hydrogen that are being like just like liberated into the atmosphere near the surface. It has no energy input, nothing. And in terms of the gaseous composition, it's 96% pure hydrogen and 4% methane. So that's like free hydrogen for whoever wants it. And I think there's a company who are now trying to extract it currently. So like I said, so attempts being made to stimulate this process at near surface conditions. There's been a lot of funding going around currently. So there's a lot of companies who've been set up and who have been funded who are looking at sort of creating serpentinization at near surface conditions to produce hydrogen. But the thing is, with hydrogen, it's a very reactive gas. It's a very light gas. So you can't like treat it like inert gases and lump it into a steel tank to be used when you need it to. Talk to any material scientist and they will spend 2 hours describing a process called hydrogen-induced stress corrosion. And it's basically reactions between hydrogen and metals, and it does very weird things. So it can absorb itself onto the surface of a metal, create fractures, and then just like destroy it. So possibly an alternative could be storage of hydrogen in underground reservoirs or depleted wells. So carbonates have traditionally served the oil industry very well in this regard, but there's really not been any assessment of how well this would work in terms of like hydrogen storage, because again, like it is a very reactive molecule. So if large-scale applications were to be undertaken, then you would need assessments about the mineralogy and the microstructures. Microstructures, why you need it is like going to be very clear as we proceed. So during my previous postdoc, we chanced upon some really interesting rocks in Alpine Corsica. So I did a bit of work here near the tip of Alpine Corsica. It's basically, if you look at it uh, from a geologist's perspective, it's very boring because it's a lot of serpentinite, and no one ever said like serpentinite is a very interesting rock. But this outcrop here, this exposure here that we worked on is interesting, not because it is a fault zone between like two different serpentinite blocks, but because it had a lot of these carbonate veins. These carbonate veins eventually ended up being tracers for hydrogen migration. And as we proceed, I will describe why. And these veins are not very uniform. So if you look at them in detail, you have a few pristine white veins. You have some with a certain degree of discoloration. You have some that are completely black. And there's like a continuous evolution from like pristine veins to these dark ones here. So the dark color of the veins is due to the presence of graphite. And it is a very weird phenomenon to have carbonate and graphite together in a rock. So we need to understand how you can create a situation where you have both carbon and carbonate in a single rock. And also, when we looked at some of the specimens, like the bottom panel here, you can see that it has different deformation imprints. So you have a part here that's sort of fractured, evolving almost into a cataclysite, and then that transitions into a very fine-grained aggregate. So there's a brittle ductile continuum almost, like even on the scale of a hand specimen. It's definitely present in the outcrop. And it's also present on the scale of a thin section. So to the left, the image to the left is a cross-polarized image, and the image to the right, where it looks like the thin section is on fire, it's an optical cathodoluminescence map. And if I look at the CL map in detail, you can see that it's not a very heterogeneous composition. So you've got these darker bits here, and they're fringed by these bright luminescent bits around here. And this is generally finer grained in terms of the fringes, but it's not just that these finer grained horizons exist. You also have some of the darker, finer grained layers here. What this does point out is that there are definitive variations in the compositions of the carbonates. It's not just like a singular carbonate with graphite that we have in the sample. So if we look at EDS maps of these domains, yeah. So if we look at the darker carbonates that we have, that's the first row here. And we can see that it's almost entirely dolomite, but there's a transition from like iron-rich dolomite in the core to iron-poor dolomite. And then there's also bits where we have dolomite with an intervening fringe of calcite, graphite, and magnetite. And then these domains evolve into these wider sort of zones, which have a lot of calcite, graphite, and magnetite, separating domains of relic dolomite. So it's very heterogeneous in terms of carbonate composition. But the question is, again, you have carbonates with graphite. So you can form that in two ways. You can cause thermal degradation of carbonates. You can just like increase the temperature to an extent where it just breaks down into carbon and oxygen. But these are sort of samples that are hosted in serpentinite. So that's not possible. The other way is by influencing the carbonates by reacting them with hydrogen. So you could potentially reduce a carbonate to graphitic carbon if you bring in hydrogen into the system. Now, the thing is, if this were to be the case, we would need to demonstrate the presence of hydrogen. It is not an easy molecule to quantify. A lot of analytical techniques that are used for geochemistry don't work for hydrogen because it is super light. But if you poke around fluid inclusions with a laser and you quantify the Raman shift, it works beautifully for hydrogen quantification. That is what we did. So we looked at fluid inclusions in the dolomite, we looked at fluid inclusions in the calcite, and it's basically the hydrogen is present in every single fluid inclusion that you see. It could be pure hydrogen, as in like this fluid inclusion in dolomite, or what was most prevalent was a mixture of hydrogen and methane. And one of the unanswered questions that I had, like I still have, is why you preserve both, because if you react hydrogen with dolomite, you should get methane. But in some certain instances, we did not. So, but that is like me preempting a question that I do not have an answer to. But yeah. So basically, we have carbonate reduction by hydrogen. We have very contrasting deformation styles from brittle to ductile flow. So what exactly happened in these samples? If you have to take a step back in terms of and sort of think of the rheology of these samples, then you look at this thin section, you've got a bit of brittle fracturing in like the area where we have the white box. There's a bit of ductile flow and a shape preferred orientation of dolomite where we have the green box. There are three important aspects that need addressing in this context. So the first bit is, how do we deform the dolomite? Is it entirely brittle, or is there a component of recrystallization? Now, dolomite is notoriously difficult to recrystallize because like it likes to form twins, it likes to break apart, but it's really sluggish when it comes to the motion of dislocations, and it needs high temperatures. So if this fine-grained bit here were to form by recrystallization of dolomite, you would need very high temperatures. Temperatures that would possibly then promote the thermal degradation of carbonate, and then the hydrogen story becomes sort of unnecessary. And then you've got these fringes here, where you've got calcite in between dolomite. Now, it could be that the calcite is growing from dolomite, it's growing onto dolomite, or it's just like a calcium-rich fluid that infiltrated the fractures, and like all of this story does not make any sense. And then dolomite and calcite behave very differently in terms of their response to stress. So deforming a dolomite-rich rock and deforming a calcite-rich rock would require very different PT conditions and stress conditions. So if we change from dolomite to calcite within a rock, we would expect a variation in the material behavior, so that also needs to be quantified. So the first bit, dolomite deformation, is it entirely brittle, or is there a component of recrystallization? So if we look at the fine-grained domains of dolomite that I described previously, you have textures that sort of resemble subgrain rotation. You've got these larger relict cores with like a finer grained fringe of dolomite. And such textures, if you were to form by recrystallization, you'd need temperatures of above 600 degrees Celsius. So we got EBSD scans from this domain. And if you take a cursory look at it, it seems that it could have recrystallized. But the thing is, once we drew a misorientation profile from like across the grain, and this is the profile along this white line, we see that there are a number of peaks, yes, but there are also like after every misorientation peak corresponding to a low angle boundary, there's a trough, so it drops off. If it were to form by subgrain rotation, then we would expect the misorientation to have a gradual gradient increasing from core to rim, but that is not what we see. Instead, we see like these constant pronounced peaks and troughs. So this led us to conclude that these were more likely low angle boundaries that represent healed fractures rather than just like proper subgrain rotation. Additionally, we also calculated the M index for these domains. So the M index is like a parameter that you can use to quantify fabric strength in your rocks. And it varies between 0 and 1. So 1 is like a single crystal direction. So it's like infinitely strong, and 0 means that it's completely random. You have no preferred orientation. So in this domain, we have an M index of 0.082, which is really low. So there's no preferred orientation. And if we recrystallize the dolomite by forming subgrains and then rotating them into newer orientations, we would expect a slightly stronger fabric than this. So it's possible that the finer grained dolomite that we see here is just formed by the fracturing and cataclasis of coarser grained dolomite grains. Now, the second bit is calcite growing onto dolomite from dolomite, or just like precipitated by an infiltrating fluid. First thing is we always see this common assemblage that's calcite, graphite, and magnetite. It's never calcite by itself, and the importance of this will be stressed later on. But first, so if I were to show you the EBSD map of this domain, then we've got a lot of like twin dolomite here, the finer grained dolomite here. But the important thing is if we look at the crystallographic preferred orientations of dolomite and calcite and this pit that I've highlighted in red, this is the CP of dolomite, this is the CP of calcite. And we see that there's a common orientation here. We plotted interface misorientations between calcite and dolomite. That's this map here. So this light blue is dolomite and the green is calcite. And we see a lot of these red lines. These red lines are boundaries between 0 and 10 degrees, so very low angle boundaries. And we see that a lot of the boundaries between calcite and dolomite are low angle boundaries. This suggests that there is an inheritance of the crystallographic preferred orientation from dolomite to calcite, and basically that the calcite grew topotactically onto the dolomite and it's not precipitated by an external fluid. The final bit is where we find a lot of calcite in our sample. So these like wider zones with a lot of calcite, graphite, and magnetite separating zones of dolomite. If we look at the EBSD maps of this domain, then we see that the CPO of calcite is like super weak. It's widely distributed without any particular preferred orientation. A very low M index value for calcite as well. And this coupled with like an average grain size of 15 to 20 microns suggests that the calcite underwent viscous flow by either diffusion creep or a component of grain boundary sliding in this domain. So you suddenly, once you form the calcite, you are creating zones where you have accelerated strain rates and like very high strain partitioning into these layers. What is also sort of noteworthy in this is we do not see so many low angle boundaries between the calcite and the dolomite, except where you have these islands of calcite in dolomite or you have islands of dolomite in calcite. But probably this is due to the fact that you disrupt initial orientation. So once you get it to flow, once you get the calcite layers to flow, you are disrupting the initial orientations that you had. Now, the thing is, you have calcite and dolomite, and it is expected that they would deform differently. But the thing is, okay, you can reduce a carbonate to graphite using hydrogen, but does it link very well to like the relationship between dolomite and calcite? So what is promoting the growth of calcite from dolomite, or what is destabilizing dolomite, let's say? To understand that, we got some perplex models done. And this basically models the effect of an initial assemblage consisting of just dolomite. And so you have temperature along the y-axis and number of moles of hydrogen along the x-axis. And if we correlate this with our observed assemblage, so we go from dolomite to a layer of like dolomite and calcite, and then you go to a domain of like calcite, magnetite, graphite. So we're going like in a path along sort of this way. What is interesting in this is there is a very strong correlation between the proportion or the dominant carbonate composition and the amount of hydrogen that is infiltrating into the system. So it's not just like an instantaneous reaction that starts as soon as hydrogen infiltrates the system, but dolomite is a stable carbonate, like with about, if you have 1 mole of hydrogen infiltrating your system, so dolomite is fine. But as soon as you cross a threshold of about 2 moles of hydrogen, then you go from dolomite being your stable carbonate to calcite being your stable carbonate. And the reason behind that is this image here in C. So this is the anchorite component of dolomite. So it is the iron part of like dolomite that you have, and that becomes destabilized after you infiltrate 2 moles of hydrogen. And it is the iron from the anchorite that is actually taken out, and that forms the magnetite that you see in every assemblage here. So it's always calcite, graphite, and magnetite, and the magnetite is formed by the destabilization of the anchorite. Yeah. So we basically go from dolomite aggregate that was like fine by itself. Suddenly, a bit of hydrogen came in, started destabilizing it. It formed calcite, and like there's still a bit of dolomite. These calcite horizons started widening, and then you created a rheologically weaker phase from a rheologically stronger phase. That sort of transitions from like brittle fracturing to viscous flow, all because like you have some hydrogen coming into the system. To summarize this bit, it's basically hydrogen's influence on the rheology of a carbonate. Now, the work that I did built upon previous work in that research group, and one of the main takeaways of that was we talk about fluid overpressure in geological settings in a very generic way, but actually fluid overpressure depends to a very large extent on the composition of the fluid. And previous work in that group demonstrated that if you have a carbon, oxygen, hydrogen fluid, you would need much less amounts of that fluid to generate the same level of overpressure compared to an H2O rich fluid. And my work basically built upon that and showed that, you know, hydrogen would also induce phase transitions between carbonates because it is a very reactive molecule. And in terms of underground hydrogen storage, like it is not going to be super feasible or convenient. So if you have a dolomite reservoir, you put in some hydrogen and 10 years later you find it's calcite and it's flowing and deforming, it's probably not going to be a good idea to do it. So this is like me skimming over the details, but a bit of self-promotion. If you want to look at it in more detail, you have the manuscript here. Now, to finish off this presentation, I would like to briefly touch upon what me and John are doing here. So our Marie Curie project is like it's abbreviated to FRIES, and it's fluid rock interactions for environmental sustainability in its full form. What we want to do is to model the hydrogen production potential from fluid rock interactions of various mafic and ultramafic lithologies from different parts of Britain. And if Dave gives me samples, then from Ireland as well. So we also know that the rocks that produce hydrogen, so typically peridotites, let's say, they're also very good at sequestering carbon. So if you've looked into Oman, you would know that peridotites there are excellent sites for carbon dioxide sequestration. So we are looking at possibly coupling this process if hydrogen production could like evolve into a setting where you also sequester carbon dioxide. So very simplistically, what we want to do is we want to model the interactions of a peridotite with like fluids of different compositions at different pressure temperature conditions to see if these interactions produce hydrogen and put in carbon dioxide into the system. So this is a sample of a peridotite or a partially serpentinized peridotite from the lizardophyolite complex that we've been working on. And we have some very preliminary models that we are currently looking at. So for example, this one here, this is a model of like fluid rock interactions between a brine, a very generic brine composition, and a peridotite composition from the lizardophyolite complex. So this model goes from like very high water rock ratios to very low water rock ratios with the fluid composition continuously evolving. So we're going from like the right to left. And in terms of like geological settings, this would be valid, I guess, for a very restricted range of geological settings, such as slow spreading ridges or something like that, but not very good for like I guess like injecting fluids into the subsurface or something like that. But what is interesting in this bit is that we do see, or our models predict substantial production of hydrogen from the compositions relevant for the lizardophyolite complex. So at 150 degrees Celsius, we're producing about 36% of hydrogen from an initial brine fluid. And what is sort of counterintuitive to me, but predicted by the models, is the proportion of hydrogen in the gaseous mixture actually decreases with increasing temperature. So once we go up to 200 degrees, then it lowers down to 20% H2, and most of the gaseous mixture is H2O. We've also done that for some groundwater compositions. So in terms of groundwater compositions, the hydrogen amount does not change substantially. So it's the same as the brine. The only difference being that at 150 degrees, there's no brucite when you use a groundwater. And at 200 degrees, it's roughly similar between a brine and a groundwater. But like I said previously, so this is not a situation that you could sort of engineer going from like very high water rock ratios to very low water rock ratios. For injection applications of a fluid into the subsurface, you would need to go from a low water rock ratio to a high water rock ratio. You would need also to use a different software package. So the previous one was SkimXPT. It does not work if you want to go in the other direction, it crashes. So this is, so we got these models using Freak-C. The problem with Freak is it is very predictive. So you have to tell it what minerals to produce. It will not tell you what minerals you might observe, which is not very good for modeling applications. So if you're trying to model something and you already tell it what to model, then it's not really good. But we do see similar trends. So in terms of hydrogen production, whether you go from right to left, so low to high water rock ratio or high to low water rock ratio, the hydrogen production amount is sort of consistent between the two models. But yeah, I guess that is where we are. Thank you.
Thank you very much, Ritabrata. Do we have any questions? Make this work.
Okay. I wanted to check that I understood what you were discussing with regard to your calcite dolomite rheology as well. So I don't know whether you could go back a few slides. Yeah, those ones happen. So you show some nice evidence, I guess, for showing that you interpret the boundaries as being old fractures. Because you just get these
this one,
profiles into science there. So but then you said that the crystallographic continuity was poor as well. So does that mean that you've got fracturing and then cataclastic flow, which has rotated the grains or particles out of alignment to give you a poor crystallographic orientation?
Yeah, so the bit where we interpreted healed fractures as low angle boundaries was like in this domain where we just have dolomite. So there's within these samples, we have domains where we have fine grained dolomite. We have coarse grained dolomite with calcite bordering those coarse grained dolomite. And then we have domains where we have dolomite that's separated by like wide fringes of calcite, so up to about like a centimeter wide. And then you have coarse dolomite, fine grained calcite. So with regard to the healed fractures, it's like these domains where we have just dolomite. And this is important because like if this were to be formed by recrystallization of dolomite, that would involve like very high temperatures and temperatures that like other work in that area would not have pointed out previously.
So those are the low, the small grain. Small grain size.
Yeah. And then the other bit was.
Did you notice that outline there is that there isn't much crystallographic continuity between them?
There is not. Yeah. It's a very.
The thought that it's fractured and then undergone some kind of.
Yes.
Right?
Yeah.
Yeah, that's fine. Yeah, thanks, Rita. That was a nice talk. This is the type of talk that when I would see as somebody studying geology in the early days, I would get like really excited about this kind of stuff. Economic geology, exploration of these types of resources, I just think is super duper cool. But it's obviously very complex. I noticed the samples that you have shown here came from the high pressure eclogite region of Corsica. Can you tell us a little bit more about when these reactions actually occurred in terms of pressures and temperatures. Obviously, whatever you observe in these types of rocks between, carbonates, graphite, and hydrogen, it's going to be very different than what you will ultimately propose for, economic exploration of sites. So, when did these reactions occur in terms of PT?
So we've modeled this at 1 GPa, which is along the retrograde path of like exhumation of these rocks. These rocks, I think, have like peak PT estimates of 2 GPa and like about 500 degrees Celsius.
Every other rock.
Yeah, I mean, whatever like matches the model, yeah. So, to your question, I think it would be very difficult to put precise PT constraints from these sort of rocks on like when the reaction happened. It is possible in some other settings, but I think like in this one, because like our models, if you think of this entire domain here, so any way you go from like a trajectory like this, you're going to get the same sort of assemblage sequence that we observe. So there's so there's almost like a 200 degrees Celsius range along which you can get the same sort of assemblages. So I don't think it is really possible to put like a precise constraint on the reaction temperatures.
Yeah, okay. Good. So 1 GPa.
Yeah.
All this is that 1 GPa, which is, if you're drilling an injection well into a carbonate rock, right? It's not going to be, you're not going to be injecting the fluid at 1 GPa. So it's going to be reacting to lower pressures, perhaps within the temperature window, maybe. So I guess the follow-up question would be, how sensitive are these reactions to pressure? Or should you expect the same type of reaction in an actual carbonate reservoir rock with pumpable hydrogen?
So I've hidden away your answer like after the thank you slide. There's a couple of more slides that have the answer to this. So if you look at this exposure here, so this thing here, it's entirely graphite. And it's a graphite rich shear zone like sandwiched between a serpentinite and an amphibolite. And for this, we definitely have good PT constraints. So somewhere between like about, I guess, 100 to 200 megapascals and about 150 degrees Celsius, because it's pure albite. It's got calcite that's been reduced to graphite. And I think based on some isotopic evidence that some other people got from there, they could constrain temperatures to like something very low, between 150 to 200. So this is actually an even more stunning example. Like, I don't have the time to cover this, but it's like a carbonate albite vein network that's become like this graphite-rich cataclysite, and it's entirely due to hydrogen infiltration. And just like one sort of point, so this is what a thin section of this vein looks like. You've got fractured albite here, you've got the graphite-rich bands here, and then you've got coarse-grained twinned calcite with graphite along the twins, and then that evolves into like a calcite myelinite. Yeah, so yeah, but like this is, I don't think we have the time to go into details on this, but yeah, there are other exposures from where we have documentation of like similar processes, but better PT constraints. Thank you.
Any more questions, anyone? Right.
Like you asked for other examples. I've never been and I don't know the composition of products, but might be trade complexes.
Where's that graph?
So I think it's Scotland.
Okay, yeah.
Yes. That was great. I love the bit about crystal inheritance because that's what I did for my PhD as well. So I really enjoyed doing that. Was that more or less a direct replacement of calcite for dolomite in terms of crystal orientations, just seeing density, but only maybe a slight change in the angle, the subduction angle?
I think in certain cases we can commit to like a direct replacement. So for example, for these ones, yeah. But in these domains, for example, it's really hard to say. Yeah, because there are some really straight angular boundaries between calcite and dolomite, but we don't see any evidence for any inheritance in these domains.
And do you think that's because, as you were saying, the more calcite you get, the more strain localization
Yeah.
you can have, and then it just removes all
Yeah.
that inheritance signal? Okay, cool. That's interesting. The other one I had, that we talked about the fluid chemistry responses to pressures,
Yeah.
between water and other types of fluids. Is that sensitivity to pressure related to the reactivity of the fluid? Because what H2O would be very different in terms of how reactive it's going to be with certain rocks. Is it
Yeah.
compared? So
Yeah.
is it just the reactivity that's sensitive to the pressure, or is there something else?
I guess from a mechanical point of view, the overpressure that you develop would also be very dependent upon the pressure that is imposed on the system. So it's not just the reactivity, but yeah.
But if you have, if you had an experiment where you have the same amount of overpressure on the two different fluids, one fluid is going to react more strongly with the rock than the other.
Yeah.
Okay. Interesting.
Yeah, that also depends, I guess, on what sort of rock you have and
Sure.
the fluid. So some fluids would be more reactive with some rocks. Because again, if I were to talk about just very briefly about these ones here. So these were albite carbonate veins that were intruded by or infiltrated by hydrogen. The hydrogen reacted extensively with the calcite, but it left no trace on the albite. So there are parts where you have albite carbonate veins, albite graphite veins, or just albite veins. Now that's the thing, the hydrogen came in, it reacted very preferentially with the carbonate and it just left the albite untouched. So I think there's a lot more work to be done on assessing the reactivity of different rocks to different fluids. So.
That's great. Thank you.
Thank you.
Unless there's anyone else, we'll leave it there. Thank you again to you.